Hello and welcome to Numeristical. We're continuing our series on machine learning for business. So in the last video we talked about metrics overall and specifically the metrics used for classification problems. This video we're going to go talk about the metrics used for regression problems, and we're going to talk about again the different kinds of predictions you can make in regression and how those correspond to different kinds of metrics that you would use to measure the quality of those predictions. So before we get into it, again, I'd like to ask you if you could please like the video and subscribe to the channel. It really helps me out a lot. And with that said, let's get into the video. Next, we're going to talk about the metrics that are commonly used for regression problems. Now, like in classification, the kind of metric you want to use for a regression problem depends on what kinds of predictions you're talking about. Now, in regression, far and away the most common kind of prediction is a point prediction. And within point prediction, far and away the most common metric is the mean squared error. Now, how does the mean squared error work? Well, it says for each data point, you take your prediction and you take the right answer, you find that distance, you square it, and then you add them all up across all the data points and take the average, divide by the number of data points. So that's what we have here in this formula. Now, this is very, very commonly used, but it's often not really what you want when you're evaluating the quality of a set of predictions. Now, why do I say that? Well, the mean squared error gives very strong penalties for big errors. So what it essentially says is, I'm willing to make lots of small errors in order to make a very big error a little bit less big. And you'll see that this often has unintended effects that are not quite what we want. By contrast, the mean absolute error does the following. It says take your prediction, take the actual value, find that distance, and just average those distances across all your data points. And this is probably what you would come up with if you were just designing an error metric from scratch. You would probably say, well, how far away am I? And on average, I want to be not too far away from the true answer. You wouldn't really think to put the square in. So this is often a better reflection of what you really want. Of course, you should always think about your particular problem and what metric really reflects how this relates to your business problem. But one of the reasons why mean absolute error is not used as much as mean squared error is that it lacks some of the nice mathematical properties that mean squared error has. Mean squared error has lots of very nice mathematical properties, which is why it is used so frequently in the training as the training metric. So if we go back to linear regression, when you use mean squared error, that math of linear regression works out very nicely. And one particular thing about mean squared error is that you're guaranteed to have a unique solution that minimizes the mean squared error in many mathematical situations. Whereas with the mean absolute error, it is often the case where there is not a unique solution that minimizes the mean absolute error. So this is one of the reasons why mean squared error is used so commonly. But I think it's important to distinguish between just because a metric works very nice mathematically and has nice mathematical properties, that's a different benefit than the metric which really reflects which sets of predictions you would prefer to have. So let's dive into these issues with mean squared error. The squared part generally does not reflect our preferences. That is, it really prioritizes reducing these big errors. And let's look at a specific example. So we've got in the first column the true answer, we've got model A's predictions, and we've got model B's predictions. And if you look at these closely, you see model A gets everything exactly right, except it makes an error of size 14 on the last data point. Meanwhile, model B is off by 1 or 2 on each of the first 6 data points. But on the last data point, it makes an error of size 13 compared to A's 14. Yet for mean squared error, which set of predictions do you think mean squared error would prefer, and which set of predictions do you actually prefer? I think most people, in most situations, I'd prefer to have Model A's predictions. I'd like to be exactly right, and then, yeah, one of these cases I have a big error. But I wouldn't prefer to make that big error a little bit less big at the cost of ruining my performance on the first 6 predictions. However, if you look at this, the mean squared error of Model A's predictions would be 196, and the mean squared error of Model B's predictions would be 178. So mean squared error actually prefers, to a considerable degree, prefers Model B's predictions to Model A's. And this, you might remember if you've studied linear regression, you talk about very influential points, and you talk about these points that are way far away, that move the curve significantly. And this comes from the mean squared error metric. So Model A is actually worse according to mean squared error, even though I think qualitatively most people would prefer Model A's predictions to Model B. If we use mean absolute error, though, this would better reflect our comparison. The mean absolute error of Model A's predictions is 2, whereas for Model B's predictions, it's 2.86. There's another issue that comes up when you talk about point predictions, and that's scaling. So in some problems, we might care more about the percentage error than the magnitude of the error. So as an example, let's consider the house price predictions on the right. Here we have a data set with 3 houses, and the true values are 250,000, 300,000, and 30 million. And here we see the predictions of 2 different models. Model A gives predictions of 245,000, 305,000, and 29.2 million, whereas B gives predictions of 210,000, 340,000, and 29.3 million. So qualitatively, you see that A does much better on houses 1 and 2, and does slightly worse on house number 3. Now, I would ask, which set of predictions do you prefer? When I look at this, I think A is doing much better than B on the first 2 houses, and it's doing a little bit worse on the 3rd house. So I should prefer Model A. But when you look at these, you see that not only is the mean squared error worse for Model A, but actually the mean absolute error is also worse. So the issue here is not so much the squared component of the error, although that does exacerbate it, but it's also that we are comparing an $800,000 error on 30 million and treating that the same as an $800,000 error on a $200,000 house. So in a problem like this, we probably care more about the percentage error. If we make a 1% error on a $30 million house, we on some level might say that should be about equivalent to a 1% error on a $300,000 house. If we don't, then we're saying the problem really reduces to who does the best on that very, very big house, because the error on that really expensive house is going to dwarf the contributions of all the small houses combined. So what's the solution, though, if neither mean squared error nor mean absolute error helps us here? The solution is to use log scaling. So if you take the log of the house prices, this is then equivalent to essentially saying the percentage error. The log changes your absolute error into a percentage error. Next, let's talk about what metrics you would use for regression if you had an interval or a region prediction. So here, what you really want to look at is the empirical coverage. You want to know what percentage of the points were inside the interval that I predicted. So often when you're at training time, when you're defining these models that give you interval predictions, you will give a coverage value, which is what you expect the coverage to be. Here we're talking about then evaluating to what extent the purported coverage actually proved to be true in reality. So you want to look at your set of test points and look at what percentage of the time did the interval or region contain the true value. Now that's one part of the prediction, but that's not the whole story, right? Because I could make intervals that are really, really wide and get 100% coverage. And that wouldn't really be that useful though, because my intervals are so wide. So the second part of that is the mean interval width, or the average length of the predicted regions. So this is kind of a trade-off. You want the average, you want to have small intervals that you're predicting, but you want them to cover the true value a lot of the time. And there's a trade-off there, obviously. As you make the intervals wider, they're going to catch more of the real points inside those intervals. Now, even the mean interval width, though, can be gamed a little bit. And how is this? Because if you look at the mean interval width, you could play a game where you say, hey, this interval's, I'd have to make this interval really wide if I want to have a high probability of catching the point, of containing the point in that interval. So what I'm going to do is, for all the cases where the interval is going to be really wide, I'm just going to predict something really, really small. And basically give up on that case, say, I'm not going to catch this case, so I might as well make a really small interval to bring down my mean interval width. So that's one caveat about using metrics like mean interval width. And this hasn't really been fully explored or fully discussed, to my knowledge at least. But one way you might try to correct this is to look only at the average width of the correct predicted intervals. So how wide were you on the ones where you actually contained the right answer? And that probably still has some flaws of its own, but the key is just to keep in mind that the mean interval width is not going to tell you the whole story because of how you might choose to game it. Finally, let's talk about when we make these density predictions that come out of probabilistic regression. So here, the standard metric is again the log loss, just like in the classification problem. But in this case, we'll use the density value instead of the probability. So if you remember with continuous probability densities, because the probability of any particular point is 0, you look at the probability density and you have to integrate over intervals to get a probability that's greater than 0. So these densities may actually have values that are bigger than 1. And because of that, the log loss could have different sign properties than you might expect in a classification problem. There's a second metric which I won't go into, but I'll tell you about, which is called the continuous ranked probability score. This is a bit complicated to define, so I'm not going to get into it here. But the way to think about it is it's a generalization of the mean absolute error, where you generalize it to the density setting. So if as your density prediction approaches a point prediction, this continuous ranked probability score is going to approach the mean absolute error. Thanks for watching. I hope you found that helpful. In the next video, we are going to discuss how to go beyond metrics and what are some of the real-world considerations you want to consider in building your model. And we're going to have a couple of case studies, some real-world examples to walk through about where metrics alone don't tell the whole story. So I hope you all find that interesting, and I hope you'll join me for that next video. Again, if I could ask you one more time, if you could please like the video and subscribe to the channel, it would really help me out. And have a great day. I hope to see you watching the next video. Bye-bye.